There's this hidden rhythm to just about everything around us. Sometimes it's a perfect, repeating pattern, like something that could just go on forever. And other times you see how things naturally fade away. Well, today we're going to decode that fundamental pulse of reality. We're talking about the physics of oscillation.
So, let me ask you this. What does a guitar string have in common with a car's suspension? I know, it sounds kind of random, right? One makes beautiful music, and the other just, smooths out a bumpy ride. But the answer is all in the physics of how they move. And trust me, if you stick with me, you're going to see that connection crystal clear.
All right, here's the game plan. We're going to start with a universal rhythm, using a really simple analogy. Then we'll see how that perfect idea stacks up against what actually happens in the real world. After that, we'll get into the formulas, the language physics uses to talk about this stuff. And finally, we'll wrap up by looking at why any of this actually matters in our day-to-day lives. So, to get our heads around this, we don't need a fancy lab or anything like that. Nope, we just need to picture something pretty much all of us have seen or done, being on a swing set. Seriously, that simple back and forth motion, that is the absolute key to everything we're about to unpack. Okay, so let's start in a perfect imaginary world for a second. Picture that swing. You give it one good push, and it just keeps going. It reaches the exact same height on each side, back and forth with perfect timing forever and ever. This is our ideal scenario, our starting point. Now, in the world of physics, this perfect, unending rhythm actually has a name. It's called simple harmonic motion, or SHM for short. Think of it as the clean, perfect blueprint for understanding pretty much any kind of vibration you can think of. And if you were to actually graph this perfect motion over time, this is what you'd get. Look at that, a beautiful, smooth, consistent wave. Every single peak is the same height, and every valley is the same depth. It's this super predictable, rolling pattern that physicists call a perfect sine wave.
So here's the really crucial part. In simple harmonic motion, SHM, the system never loses any energy. We're pretending there's no air resistance, no friction in the chains of the swing, nothing. It's a totally closed system where all the energy is perfectly conserved, and that's what allows the motion to just keep going forever.
This graph also helps us name a key part of this whole thing, that peak height. That's called the amplitude. It's basically the highest point the swing reaches on either side. And in our perfect world of simple harmonic motion, that amplitude never ever changes. It hits that same exact high point over and over and over again. But of course, that's the ideal. We don't live in a perfect, frictionless world. In reality, right, every motion eventually fades out. So now let's bring it back to Earth and see what happens when we add the real world back into the mix.
So, back to our playground. We all know that if you push a swing, it eventually slows down and stops. Why? Well, every single time it moves through the air, it's losing a tiny bit of energy to air resistance. The hinges on the swing set, they create friction. All these little forces are actively working against the motion.
And here's what that looks like on a graph. See the difference immediately? The wave starts out nice and strong, but with each swing, the peaks get lower and lower and lower. The amplitude is shrinking. This right here, this is the visual fingerprint of a system that's losing energy.
So this real-world version has its own name too. It's called Damped Harmonic Motion, or DHM. And that word damped, it sounds technical, but it really just means any effect, like friction or air resistance, that pushes back against the motion, making it lose energy and, eventually fizzle out. Okay, putting them side by side like this. Wow, it really makes the difference obvious. On the left, you've got that perfect, ideal world of SHM. It's constant, it's clean, it never ends. And on the right, you've got the real world of DHM. It's a story of decay, of energy slowly bleeding away. So let's just break it down really simply. Ideal motion, SHM, energy is conserved, amplitude stays the same. Easy. Real motion, DHM, energy is always being lost to stuff like friction, and so the amplitude gets smaller and smaller until it stops. Okay, so how do physicists actually describe this stuff? How do they predict it? Well, they use a special kind of language, really, made up of just a few key variables. Let's go ahead and meet the cast of characters. Now hold on, don't worry. We are not about to solve this whole problem right here. I just want you to see it, because it helps us pick out the key pieces of the puzzle, the information you need to understand any oscillating system from a simple spring to a super complex electrical circuit. All right, there are really just three main players here. First up, you've got M for mass. In our analogy, that's just the person on the swing. Then there's K, the spring constant. That's basically the springiness of the ropes, how strongly they try to pull back to the middle. And finally, there's B, the damping coefficient. That's our catch-all for anything that acts like a brake, like the air resistance that's trying to slow the whole thing down.
And here's the cool part. These three are locked in this constant dance. The springiness, K, is always trying to pull everything back to the center. That's the restoring force. But the mass, M, has inertia, right? It doesn't want to stop on a dime, so it always overshoots the middle. And the whole time, our damping, B, is playing the role of the brake, just constantly taking a little bit of energy out of the system, slowing it all down.
So you might be wondering, why are we spending all this time on imaginary swings and wavy lines? Well, here's why it matters. Because this rhythm, this oscillation, in both its perfect form and its real-world decaying form, is, and I mean this literally, everywhere. Hey, remember that first question I asked? A guitar string and a car's suspension? Well, a guitar string vibrates to make sound. That's an oscillation. And a car's suspension? That's a brilliantly engineered damped oscillation. It's designed to take the hit from a pothole, absorb that energy, and stop bouncing immediately. And it doesn't stop there. This same idea is used to protect skyscrapers from earthquakes, to keep time in a watch. It's even in the electrical circuits that power your home. This stuff is absolutely fundamental. And really, that's the big takeaway here. This simple back and forth. This little dance between a force pulling something back to the middle and its own inertia, and then that slow, inevitable decay, that is truly the hidden pulse of our world. It drives so much, from things in nature to the most amazing technology we've built. So, that leaves us with one last question to chew on. If everything in the real world is damped, if every swing eventually stops, then how on earth do we create things that need stable, lasting rhythms? How do we build a clock that keeps perfect time, or get a musical instrument to hold a note? Well, that's a fantastic question, and the answer is a story for another time.